Out of the thousands of mosquito species on our planet, if you had to cast a villain for a global health thriller, well, this one would be your star. Meet Aedes aegypti. It looks tiny, almost delicate, right? But this little insect is responsible for spreading some of the world's most feared viruses. We're talking dengue, yellow fever, chikungunya, and Zika. It's pretty much public enemy #1 on a global scale. So what is its secret? What makes this one species so incredibly good at its terrible job? It's not just random chance, that's for sure. There's actually a science to being a superspreader, a very specific formula that turns an insect into a massive public health threat. And that formula has a name. It's a concept that scientists use to figure out the risk of an outbreak, and it is the absolute key to understanding the secret weapon of Aedes aegypti. It's called Vectorial Capacity. Now, I know that's a mouthful, but all it really is the scientific recipe for an outbreak. It's just a way of measuring exactly how efficiently a disease can spread from a vector, like our mosquito, to a host, like you and me. And this is its blueprint. Now, I know what you're thinking, a math equation, but hey, don't worry, we're not going to do any calculus today. Just think of this as a list of ingredients. If we can understand what each letter stands for, we can decode precisely why Aedes aegypti is so dangerous. So let's do that. Let's break this thing down variable by variable and see how each piece of the puzzle contributes to this mosquito's super spreader status. First step is M. This stands for vector abundance. It's actually pretty simple. How many mosquitoes are there for every person in a given area? It makes sense, right? The more mosquitoes you have buzzing around, the more chances there are for a bite, and the more opportunities a virus has to jump from one person to another. Okay, next is A, the human biting habit. This one measures a couple of things: how often a mosquito likes to feed and how much it prefers human blood. Does it bite every few days, and does it specifically seek us out, or is it just as happy biting, say, a bird or a dog? For a disease to spread among people, a mosquito that loves biting us is way, way more dangerous. And this A variable is absolutely critical. You see, in the formula, this one is squared. That means its impact is exponential. A mosquito that bites people just a little bit more frequently doesn't just raise the risk a little, it raises it a lot. So yeah, this biting habit is a huge deal for transmission. Then you've got P for daily survival probability. To put it simply, how long does the mosquito live? A longer lifespan means more chances to bite, more chances to pick up a virus in the first place, and, of course, more chances to pass it on to somebody else. And finally, we have Quin, the extrinsic incubation period. This is the time it takes for a pathogen, like the dengue virus, to sort of activate inside the mosquito after it drinks infected blood. The mosquito has to stay alive for this entire period to be able to transmit the virus. And what's really fascinating is that this is hugely influenced by the environment, especially temperature. Hotter weather can actually speed this whole process up, making the mosquito infectious much sooner. Okay, so we've got the blueprint, right? We have the ingredients. But how does Aedes aegypti manage to crank every single one of these variables up to 11? Well, it turns out this mosquito has perfectly adapted to our modern way of life. This slide really lays it all out. Aedes aegypti loves us. It lays its eggs in our flower pots and old tires. It feeds almost exclusively on people, which is a massive boost for that all-important A variable. It doesn't just put up with our houses, it actually thrives in them, resting indoors, even mating indoors. This whole domestic lifestyle keeps its population high right where we are, guaranteeing it's always close to its favorite meal. It's a true master of city living. So, the case seems pretty closed, doesn't it? We have a mosquito that's perfectly evolved to live with us and spread our diseases. But there's a twist in this story, because it turns out vectorial capacity isn't just about the mosquito's biology. It's also about our behavior. And that brings us to this fascinating real-world case study. We're looking at two cities right on the U.S.-Mexico border, Laredo, Texas, and Nuevo Laredo, Mexico. They're separated by just a river. They have the same climate, the same mosquitoes, but they have two completely different stories when it comes to dengue fever. Now check this out. It's a total paradox. Laredo, on the U.S. side, actually has a high number of these dangerous mosquitoes, but a very low rate of dengue. Meanwhile, Nuevo Laredo has fewer mosquitoes, but a much higher rate of the disease. So, wait a minute. How can the place with more of the super spreaders have less of the spread? The answer, it turns out, is lifestyle. In Laredo, things like widespread air conditioning and modern houses with screens on the windows mean people just spend a lot more time indoors, physically separated from the mosquitoes outside. That simple change in our behavior breaks the transmission cycle. It dramatically reduces that effective biting rate, which causes the vectorial capacity to just plummet, even when there are plenty of mosquitoes around. So, here's the real key takeaway. Vectorial capacity is like a dynamic dance. It's not some fixed number that's only based on an insect's biology. It's this complex, always changing relationship between the vector, the pathogen, the environment, and, maybe most importantly, us, the hosts. And that leaves us with a really critical question for the future, doesn't it? As our world gets warmer, potentially speeding up that virus incubation time, and as more and more people cram into dense cities, how is this fragile balance going to shift? The story of the super spreader, it turns out, isn't just about the mosquito. It's also about the world that we are building all around it.